Welcome, this is the video for section 2.7 for AP Calculus, Limits at Infinity. We're wrapping up our discussion of limits here, and now we want to start talking a little bit about really end behavior and what goes on when we put really large or really small numbers into a function. So away we go. Like I just said, we've considered limits a lot as x approaches that specific point C. Right, and for those situations, we've said that, usually all you got to do is plug in, and if you get a number, go with it. If you get something else, then you maybe have to do some manipulations, factor and cancel, look if there's some sort of vertical asymptote, maybe the limit doesn't exist, maybe there's a hole. But what about when x tends to infinity, or tends to negative infinity? That's what we want to look at in this section, and as I said before in class when we did the calculator activity, we're talking about the end behavior of a function. We did a little bit of that in Algebra 2. I'm sure you did it as well as in pre-calc. We're going to build on some of those notions of end behavior. Remember, we just talked about it for polynomials, and we said there were 4 different cases. Remember, we said if we have an even polynomial with a positive leading coefficient, the end behavior looks something like that. If we had an even with a negative leading coefficient, the end behavior looks like this. If we have odd with a positive, well, then the end behavior looks something like that. And odd with a negative leading coefficient, then it was the opposite. And now we can actually use some limit terminology for each of these. So in this case, we can say the limit as x approaches positive infinity equals infinity. The limit as x approaches negative infinity equals positive infinity. And if you want, it might not be a bad idea to try to fill in limit statements for the other 3 at some point to have in your notes, because the example problems that we do aren't going to be about straight up polynomials, because honestly in calculus the assumption is you already know this because you've worked with polynomials your entire high school career, so you should have a gist of what end behavior of polynomials are. I want to look at some more complicated functions, and that's what this video is going to be strictly about. If this concept right here, though, that I am just asterisking is causing you trouble, you need to come talk to me, because I'm assuming that you know this. Okay, so just some notation from the last slide. So we say the limit as x approaches infinity of f of x equals a value called L if your function gets closer and closer and closer to that value L for larger and larger values of x. Okay? And then likewise with the negative infinity, the limit as x approaches negative infinity of f of x equals a value L if your function gets closer and closer to L for, sorry, that's a typo, it should be smaller and smaller values of x. Okay, so we're really talking about just really big x's, really small x's. Can we come up with a pattern of where the function goes? Another phrase that I want you to understand, and you've seen before in Algebra 2 and Pre-Calc, is the concept of a horizontal asymptote. We call the line y equals L a horizontal asymptote if that value L is either the limit as x approaches positive infinity or x approaches negative infinity. Couple things to note and to be mindful of, because it's going to come up in some of the homework problems I assigned. First off, and we saw this when we did some practice AP problems, a function can cross a horizontal asymptote, unlike a vertical asymptote. Remember, we're only looking at really big or really small values of x. So when x gets really large or really small, like in these 2 areas, that's when we start to get close to the line but not go over it. But in the middle, anything can really happen. The other thing that I want you to pay attention to, and this picture I got from your textbook, it's a great picture because it proves this point about crossing the line, and it also proves that a function can have 2 horizontal asymptotes. In the case of this function, which they define as g of x, notice that the limit as x approaches positive infinity is 7. So we have a horizontal asymptote at y equals 7 for the big values, for the big x's. But then we also have the limit as x approaches negative infinity of f of x comes to be positive 3. So we also have the horizontal asymptote of y equals 3, and that's for small x's. Okay, so it's quite possible. Sometimes the positive and negative infinite limits go to the same value, in which case you just have one asymptote, but get used to the fact that it could be one or both. So when I ask you, hint, hint for some of your homework problems, what is a horizontal asymptote of a certain function, you really should be doing both of these limit problems to figure out if there's more than one asymptote. Don't be lazy and cut corners and just do one limit and assume that's the only asymptote, okay? So let's talk about how we find these limits and find these asymptotes. I'm pretty sure I put this in one of your summer assignment videos, but I'm going to do it again. What we need to do is we need to compare the degrees of the top and bottom polynomials in our rational functions. More often than not, infinite limits will take the form, infinite limit problems, that is, will take the form of a rational function where you have a function up top and a function on the bottom, and you want to compare what happens for really large and small values of those functions. Now, your book goes through a very long description of how to get to these rules, but I kind of want to simplify it for the sake of this video. You compare the degrees. If the bigger degree is on the bottom, then that means as you put bigger and bigger values, it's going to overshadow the top. So the limit's going to get closer and closer to 0. Think about fractions, right? 1/2, 1/3, 1/4, 1/5. As you keep increasing the number on the bottom, the fraction gets smaller and smaller until it gets closer to 0. Well, the same thing is kind of at work here with polynomials. A small degree over a big degree gets you a limit of 0. If you have a big degree over a little degree, then you're either going to be going off to positive or negative infinity. I can't definitively tell you one way or another. What you have to do for each problem where this happens, you have to look at the signs in the problem and just play around with either large or small numbers and see, are the numbers getting bigger or are they getting smaller, in which case it's positive or negative infinity. Or rather, are the numbers positive or negative? That tells you if it's positive or negative infinity. Excuse me. We know they're going to be getting really big or really small if it's going to infinity. Finally, we want to look at if the degrees are exactly the same. Well, then all you do is you just look at the leading coefficients. That fraction is the value of the limit. Okay? So in the case of 2x squared over 3x squared, the limit would be 2/3. So let's do a bunch of examples of this. So we've got the limit as x goes to infinity of 4x squared plus 50 over x cubed minus 85. So again, we look at where is the bigger degree. Biggest degree is on the bottom. So that means the bottom function is going to dominate when I put larger and larger numbers. So that means the function is going to get closer to 0 as we put in larger numbers. So there's your limit, and there's at least one horizontal asymptote for this function would be at the line y equals 0. And we could write that if we want. Now, what happens if we have this second example? The limit as x approaches infinity of 4x cubed minus 5x squared plus 3x minus 1 over 5x cubed minus 7x minus 25. Okay, again, we have a tie. I have a cubic over a cubic. So when that happens, the leading coefficients kind of give me the answer. The limit has to be 4/5. So we have a horizontal asymptote at the line y equals 4/5. Now let's look at what happens when we have a bigger function over a littler function. Now we said that it could be either positive infinity or negative infinity. We have to check the values. So this is a limit as x approaches negative infinity. So we're putting in negative numbers into this function. So let's look at what happens to the sign of the number. If I put in a negative number here and we cube it, I still get a negative number. Minus 23, I'm going to have a negative up top. If I put a negative number times 4, minus 1, I also get a negative number. Negative divided by negative yields a positive, so the limit has to be positive infinity. Okay, does that make sense? I hope it does. You'll see something like that in the homework. If you need to, please ask me questions about it. Okay, if we were going towards positive infinity here, well then I'd have a positive over a positive, and the limit would still be positive infinity. Okay, let's look at the last one. The limit as x approaches negative infinity of 4x minus 5x squared plus 3 over 1 minus x. Well, This is a little bit interesting because we're dealing with a complex fraction. Why don't we try to change this? Why don't we multiply top and bottom by x? Now, the denominator becomes 1. This becomes 4x squared minus 5x cubed plus 3. Well, this just becomes a polynomial. I'm just trying to figure out what's the limit of this cubic polynomial when x goes to negative infinity. We'll go back to what we did at the very beginning of the video. We've got an odd polynomial with a negative leading coefficient, so the picture looks a little something like this. So, on the left side, as x gets smaller and smaller, the function gets closer and closer to positive infinity. So that's going to be your limit there. Okay? Okay, so now what I want to do is I want to keep going and dealing with rational functions, but I want to make one of the two functions have a radical in it. Now, when you're dealing with radicals in these limits to infinity problems, you can still handle it with the same rules that we did. You just have to finesse it and realize what they're actually saying in terms of the exponents. Okay? So in the case of this first one, the limit as x approaches infinity of the square root of x squared minus 3x over 2x plus 1, I still want to compare my highest degree to my highest degree here. But remember what the square root of x squared is. It can be either positive or negative x. That's important for when we come to figure out what the sign of our answer will be. All right? So that means this is basically like x over 2x, the limit as x goes to infinity of that. So we really have our tie again, so we're going to use 1/2 to be our limit. Or are we? We just want to double check and make sure it's positive 1/2 and not negative 1/2. And the way we would do that is we would put a positive number up top and a positive number down the bottom. So if I put a positive number up top, well, if I'm going to take the square root of it, it's got to be positive as the answer. A positive here would keep that positive, 2x plus 1. So a positive up top divided by a positive on the bottom would mean that 1/2 would have to be the infinite limit as x approaches positive infinity. Now, negative infinity, again, it's the same function that I did here, but just to prove the point, again, we're basically looking at the limit as x goes to negative infinity of x over 2x. So that would be 1/2. But we have to go back to the original problem and check, when I put negative numbers in the original problem, do I get positive values or negative values? Well, when I put a negative in here, I'll get a positive and then another positive, so the square root of that will be positive. But down here, if I put a negative in for 2x plus 1, I get a negative. So I've got a positive over a negative. That's going to give me a negative function value. So that must mean that this limit is going towards negative 1/2. So here's the punchline of that. If I asked you what the horizontal asymptotes of this function are, there are two horizontal asymptotes. There's one at y equals 1/2, and that's where the larger values are going. And then there's another one at y equals negative 1/2. So basically, your picture might be a little something like this. You might have something where basically you've got one asymptote going that way, and you've got another one going that way. Oh, shouldn't really cross, but you get the gist there, okay? Last thing I want to talk about are some other weird functions. So you have one similar to this in the homework, and I just want to make sure you understand it. There's one key limit that the book doesn't talk about in this section, an infinite limit, that I want to make sure you understand. And it's one involving e to the x, okay, and really any exponential. When you put really, really small values of any exponential, you end up getting closer to 0. Because think about it. E to the negative 1 is 1 over e. E squared, 1 over, or e to the minus 2, 1 over e squared. Okay? You're putting smaller and smaller and smaller fractions there. So that limit must be getting closer and closer to 0. This might be something to put on a flashcard. Okay? For the heck of it, even though it's not important for this problem, the limit as x goes to positive infinity of any exponential would be positive infinity. Okay? So in this case, if I want the limit as x goes to negative infinity of 4 plus e to the 3x over 7 minus e to the 4x, well, when we're putting in really, really, really small values for these x's, both of these e's just really turn to 0. So in this case, the limit would just be the constants, 4/7. Kind of neat. Okay? And the final thing I want to draw your attention to, and we'll be coming back to this more and more often throughout the year, is this concept of dominance with respect to these infinite limits. And what I mean by that is so far we really only talked about, with the exception of that last example, strictly polynomials. What happens if we have limits that are rational functions that contain other classes of functions, like exponentials and logs and things like that? So here's kind of the rule. All right, the order is kind of EPL, if you will. Exponentials dominate polynomials. And what we mean by dominate is they kind of behave like the higher degree, the big over little. This would be the big, the polynomials would be the little. Polynomials dominate over logs. And then if you have more than one exponential function in your rational, the one with the higher base dominates over the lower base, the same way like higher powers of polynomials dominate over lower powers of polynomials. Also a concept to kind of want to know and maybe put on a flashcard. Here's what I mean by that, and I've seen this. This is a question that I found on a released test. The limit is x goes to infinity of x cubed over e to the 4x, okay? And this is something similar to something that's been on a past test. Now, we can't use the big over little with respect to degrees because this is not a polynomial, it's an exponential function. So if we use this concept of dominance, since the exponential dominates over the polynomial, basically it's sort of like the little over big situation that we saw earlier in the video. And when that happens, the limit as x approaches infinity has to be 0. Okay? Just a little food for thought when you're dealing with some other functions that are not just polynomials. All right? There should be plenty to get you going on infinite limits. Try the homework problems. Talk to me on Monday if we have any questions. Feel free to email me over the weekend as well. Keep going. We're almost done with limits, and very soon we'll be getting into the next really exciting component of calculus, and that is derivatives. We're really going to do some heavy-duty calculus coming soon. All right, enjoy your weekend, and I will see you on Monday.